we were talking about binomial random variables. So we talked about identifying a binomial setting using our four conditions. So are there two outcomes, which we labeled as a success and a fail? Success meaning what we're looking for, fail meaning anything else. We talked about trials being independent. And then we talked about at the very end, I kind of rushed through it, but that independence, when we sample from a finite population, can sometimes not be met. So like anytime I'm sampling from a finite population, I'm technically violating that independent condition. But we said as long as the sample we take is less than 10% of the entire population, then we're okay to proceed under the assumption of independence. So basically what we're saying is we know the probabilities are going to change from one trial to the next, but it's going to be a small enough change that it's not going to affect the overall value enough. Okay, so that's kind of the main idea behind it. So when we're working with those, that independence assumption is extremely important. And so whenever we do sample from a finite population, we got to be really careful with that. Make sure we verify that 10% condition is met so that we can still assume independence throughout the process. And then the big thing with binomials, because this is what defines a binomial versus a geometric, was that we have a fixed number of trials. So we are going to set the number of trials we're going to run ahead of time, and then within that set of trials, we're going to look for a number of successes. So it might be an exact number of successes, it might be a range of successes. And so we talked about on the calculator, using that binom PDF, using the binom CDF for the different scenarios. And then the last thing was that probability of success needs to stay the same. So with geometric random variables, we have almost an identical set of conditions to check, but the main difference between a binomial and a geometric is that in a geometric setting, we do not have a fixed number of trials, because what we're going to be doing is we're going to continue to repeat the random process over and over until we find a first success. So that's kind of the key here. So in a geometric setting, we're only going to have two outcomes still. It's going to be a success or fail. We still need independence. We still need the probability of success to be the same throughout. But as it's highlighted here then, the main difference is that third condition. Yesterday it was we have a fixed number of trials, and we were looking for a specific number of successes. Today, with the geometric setting, we're going to say we're going to keep doing the random process until we find a success. And so when we think about these geometric settings, okay, the whole idea of independence again is extremely important. Now, with these geometric settings, that 10% condition doesn't apply, because in the binomial, I knew exactly how many people I was going to select, or I knew exactly how many trials I was going to conduct. And so I could make sure that those trials, the number of people I selected, was less than 10% of the total population. With a geometric setting, we don't have that ability. We don't know how many we're going to have. So we're going to continue the random process until something happens. So we don't know if it's going to stay below 10% or go above 10%. So in this case, that independence assumption is extremely important. We don't have a way to skirt around it because we don't know for sure what's going to happen as we go through this process. So as far as the types of problems we're going to be doing, it's going to be a lot like what we did yesterday. It's going to be, here's a scenario. Is it geometric? So can we check the four conditions? Are they all met? If one or more of the conditions aren't met, we make sure we specify it's not geometric because this is happening, so it's not independent. We have a fixed number of trials. There's more than two outcomes, whatever the case may be. So the first thing is just being able to identify that geometric setting. So as an example, this is a scenario we talked about before back in the first half of the unit. We talked about simulations. And so the example we used was that cereal company putting cards in their boxes of cereal. So they had 20% of the boxes contain a picture of Tiger Woods, 30% David Beckham, the rest had Serena Williams. So now in this setting, So what we're trying to determine here is if we have a geometric setting. We're a huge Tiger Woods fan, so while we don't care about the other cards, we want to get a photo of Tiger. Okay? So what we want to know is, how many boxes do we expect to open before finding that card? So as we look at this setting and we're trying to determine if it's geometric or not, when we think about what's happening here, first thing we ask ourselves is, do we have two outcomes? So can I define a success and a fail? And so if I was thinking about this, what would a success look like? We get Tiger Woods. A fail would be either of the other two, okay? So even though there's 3 different cards, we're only looking at 2 outcomes. Either I get Tiger or I don't. Would opening the boxes of cereal be independent from one another? Yeah, whatever we get from the first box isn't going to dictate what we're going to get in the next box, right? So we have independence. Are we looking for a first success? Yeah, we're saying how many boxes, how many trials do I have to perform before I find a Tiger Woods card? So we're looking for that first success, and then the probability of success will be the same throughout. So because we've already established that independence, the probability of success of 20% would remain constant throughout. Okay? So then the next thing is, once we know we have a geometric setting, what is that model going to look like? So starting off, we're going to talk about the mean. When we have a geometric setting, when we ask how many trials before we expect a success. So in this particular scenario, it says how many boxes might we expect to have to open before we find that Tiger Woods card. And so we did this using simulations. Like when we first introduced this example, we actually performed a simulation where we generated random numbers and we continued the process until we found a specific result. And then we did that through multiple trials. And then we took the number of trials it took, or the number of boxes it took to get it each one, and calculated an average. So we calculated an estimated value. Now we have a way to calculate the exact value. So if I have a 20% chance of getting Tiger Woods, so that's like a 1 in 5 chance if we think about it in terms of a fraction, we should expect to get a Tiger Woods card on average in the 5th box we open. And so when we calculate this expected value, what we notice is that that expected value always ends up being 1 divided by my probability of success. So for our geometric settings, when they ask for the mean, when they ask for the expected value, we simply take 1 divided by the probability of success and then interpret the result. When we look at the model overall, so much like we did yesterday with the binomial model, this model is much simpler. And it's really intuitive when we think about what we're looking at here. So when we look at the mean and standard deviation, we just discussed the mean. So 1 divided by the probability of success. The standard deviation then, because anytime we have a mean, we want a standard deviation to accompany it. These are 2 formulas you will not need to memorize. They will be given to you on that formula sheet. You just have to know when and how to use it. And so if we think about what we're looking at here, expected value, 1 divided by the probability of success. For standard deviation, we're taking the square root. 1 minus p represents what? The probability that we fail, right? So if I know what the probability of success is, when I go to calculate standard deviation, I'm taking the square root of the probability that we fail divided by the probability of success. And then the interpretation is the same as any other standard deviation interpretation. Over numerous trials, the value we find will typically differ from the mean by this amount. And then as far as probabilities go, so yesterday with the binomial, we had that n choose x. p to the x times 1 minus p to the n minus x. We looked at that as the probability of successes to the number of successes, probability that we fail raised to the number we fail. In this case, it's quite a bit simpler. And when we look at kind of what the formula looks like and think about what it means, what we're saying here is the probability that my random variable takes on a specific number. So like for the Tiger Woods example, if I wanted to calculate the probability that the first Tiger card that I get is on the 5th box, so the probability that my first success happens on the 5th trial, if I think about that, that means that I had to have failed 4 times. So I'm going to open 4 boxes and fail, and then that 5th box that I open, I finally get what I'm looking for. And so much like yesterday, this formula for calculating probabilities is just a simplified general multiplication rule. If I have that probability that I fail, I need that many fails. And then I'm going to succeed on the exact trial that I'm looking for. So there's going to be 1 success every time. So when we're calculating these probabilities, whatever trial we're looking for, I need to fail that many times minus 1, and then I succeed on that very last try. So it's just a way of shortening up or streamlining that general multiplication rule. So if we look at an example, so Postini is a global company specializing in communication security. They monitor over 1 billion internet messages per day and recently reported that 91% of emails are spam. So 91% of emails that get sent to inboxes are spam. So the first question says, assuming that your email is typical, and let's say you're not using spam filters, if your inbox collects mail overnight, about how many spam emails should you expect to have to go through before you find a real message? So this first question is asking us to calculate the expected value, calculate the mean of this distribution. So the first thing we have to establish is, are we geometric? So do I have 2 outcomes in this scenario? Yes. What's my success? A real message. Fail would be spam, right? So we have 2 outcomes. Would emails be independent of one another? Yeah, the email you receive first is not going to dictate what you receive second or third or fourth. So every email that you receive should be independent of the others. Are we looking for a first success? Yeah, we're looking for how many emails before I find that first real message. And then my probability of success will remain the same throughout. So the next thing after I establish that we're geometric, I need to actually define my random variable. So if we just use our generic x, when I define my random variable this time, we're looking at the number of emails we open until we find a real message. So just like yesterday, we need to define the random variable, specify exactly what it is we're looking at. So we're looking at the number of emails we open until we find a real message. Yesterday then, we would have also defined the number of trials we were using as well as the probability of success. In a geometric setting though, we don't know how many trials it's going to be. That's what we're trying to figure out. So the only thing we can define is that probability of success. And so for this setting, we said a success was getting a real email. What's the probability that we get a real email? Would be 9%, right? If there's a 91% chance I'm getting spam, there's a 9% chance I'm getting a real email. So, using the formula, It says find the expected value. How many messages do we expect to have to go through before we find a real email? So based on the formula, I would take 1 divided by my probability of success, which in this case is the 0.09. So if we plug that in our calculators, about 11.1. So 11.1 messages. So if we were to check many mornings, we check our inbox, on average, we would expect to have to go through 11.1 messages before we find a real message. So calculating and then also interpreting. Okay. That second question, what's the probability that the 5th message in your inbox is the first one that isn't spam? So when I go to calculate this, the first thing, we need to make sure we have the correct notation. So if I want to write the probability that the 5th message in your inbox is the first one that isn't spam, what would that look like in terms of notation? What am I trying to calculate here? That x equals 5. My random variable takes on the value of 5. So we're calculating the probability that x is equal to 5. And so with the formula, what that looks like is if I want the 5th message to be the first real message, that means I need to find spam on the first 4. So the probability that I find spam is 91%. I want that to happen 4 times. And then I find my real message. So the probability that I fail raised to the number of times I need to fail times the probability of success on that last trial. And so if you plug that in your calculators, what do we get for a probability in this case? .0617. Okay. So what we're saying is, on any given day, the probability that the first real message is the 5th one that we open is about 6.17%. Now, just like yesterday then, I can use the formula, and with this geometric model, if I'm looking for an exact percentage, this formula is actually pretty simple, pretty easy to plug in and do. I typically use the formula for a situation like this, okay? But just like yesterday, we do have a function on the calculator that'll do this as well. So on your calculators, so on our calculators, if we want to do the same exact example or the same problem, we go into our distribution menu, so go to your second vars. We scroll up. And in this case, the 2 functions we want are right there. So the minute we scroll up, we've got our GeoMet or PDF, GeoMet CDF. Much like yesterday, and you might want to write this down just to remind yourself, the PDF, so GeoMet PDF, is when we're looking for a specific number of successes. Or not a specific number of successes, a specific trial. So I'm looking for the first success to be on this specific trial. So when my notation is the probability that x equals some number, I'm using PDF every time. And then just like yesterday, the CDF is going to be less than or equal to whatever trial I'm trying to find that first success on. So if I have a less than problem, I can use that CDF. I want to know what's the probability that I find a first success within this many trials. So it could be the first, the second, the third, up to where I want to actually find that first success. So PDF, exactly on the trial that I want. CDF within the number of trials that I want. So in this case, we would choose the PDF option. And then there's only two values to plug in here. It just needs the probability of success. So for a real message, that was 0.09. I want it on the fifth trial, so X value is 5. And then just like yesterday, if you choose this option, you would take this and copy it onto your paper. So even if you're using the calculator, you still have to tell me exactly what you're doing. So you'd write GeoMet PDF, 0.09 for P, 5 for X. And then when we hit enter, we get the same value that we found earlier. Okay, so this would be another option you could use. So whether you use the formula or the calculator, just make sure you show me exactly what it is you're doing. Again, for the PDF option with GeoMet, I typically just use the formula, but you can always use the calculator if that's more comfortable for you. Then, back to my example here. So same scenario. This time we want to know what's the probability that the first real message is found before the fourth message checked. So again, first thing we got to figure out is the notation. What is it I'm trying to calculate here? So I want the probability that the first real message happens before the fourth message is checked. So what would that look like in notation? The probability that X is less than 4. So now in this case, if I wanted to attack this using the formula, just like yesterday, I have to think about every possible outcome that could happen here. So if I want it to happen in within the first 4 messages, we're saying it could be the very first message. So I could use the formula to calculate that. Then I would have it on the second message or the third message. Those would be the 3 scenarios I need to figure out. So I'd run the formula 3 times, add the 3 results, and get my overall probability for X less than 4. Or in the calculator, this is where we would use that CDF function. So on the calculator, if you go into second vars, scroll up, select your GeoMet CDF function. We plug in our probability of success being 0.09. And then just like yesterday, this is where it gets a little bit tricky. You got to think a little bit. We want the probability that X is less than 4. The calculator is going to calculate up until the point we tell it to stop. So if I want X to be less than 4, where do I need the calculator to stop at? 3. So again, the number might match the X value. It might not, depending on what we're looking for here. So GeoMet CDF, 0.09, stop it at 3. And then when you hit enter, what do we get for a percentage, or what do we get for a probability? What? 246? Okay. So there's about a 24.6% chance that the first real message found happens before the fourth message checked. So either on the first, second, or third. And then our last scenario, what's the probability that the first real message doesn't happen until after the 8th message is checked? Now, when we had a situation like this, yesterday, so now we're saying what's the probability that x is greater than 8. So when we did this yesterday with the binomial, this was like when we did our table A with normal distributions earlier. Binom CDF can only calculate left. Geomet CDF can only calculate left. And so yesterday we used that complement rule to attack a greater than problem. I would do 1 minus binom CDF, number of trials, probability of success, when do I want it to stop. Okay. As far as today goes, much easier process. If I want the probability that x is going to be greater than 8, and I think about what this is that I'm actually looking for, basically what they're asking is, what's the probability that we fail 8 times? After that, we don't care what happens. So I don't care when we find the first message. We just need to make sure we fail 8 times before we do. So as far as a calculation goes, I don't need to use a complement rule. I can do 1 minus Geomet CDF if you want to, but in this case, all I need to do is calculate the probability that I fail 8 times. After I fail that 8th time, I don't care what happens after. So we put that 0.91 raised to the 8th, and then whatever that comes out to be. So with these problems, we got that mean and standard deviation formula. The probabilities, if you're doing a PDF problem, so an exact number of trials, you can use the formula, use the PDF, doesn't matter as long as you show what you're doing. Less than, we want to use the CDF function. And then any greater than problem, all I got to do is make sure I fail the specified number of times, and that's it. Anything after that can happen, so we just calculate that probability that way. And that's it for geometric. So here are the problems I want you to try out.